The reaction quotient is really a quantitative application of Le Chatelier's principle, and we'll look at a simple case where the concentration of a reactant is increased at a constant temperature. So when the concentration of hydrogen is increased, for example, then the system responds by shifting the reaction to the right. So the excess reactant, H2, gets consumed, and this results in the other reactant being consumed also, while more of the product gets produced. So at our next state of equilibrium, the concentrations of the reactants and products are constant. And similarly, when we look at the rate of reaction versus time, you have an initial jump in the forward reaction due to the abrupt increase in concentration of a reactant, and as the excess reactant is being consumed to form new product, the rate of reaction decreases in the forward direction. And then when more product is formed, this is consumed in a backward reaction. So in the next state of equilibrium, the rates of reaction are equal in both directions. So at equilibrium, the reaction quotient is equal to the equilibrium constant, and when a system was stressed with the excess reactant, there's more reactants than there are products, so therefore the reaction quotient is less than the equilibrium constant in this case. So the system basically responds to restore the reaction quotient to be equal to the equilibrium constant after a stress is applied to a system that's initially at equilibrium. A change in temperature can also cause a change in the equilibrium constant. So if we consider this exothermic reaction, we add heat as a product, and using the reaction kinetics, an increase in temperature is going to cause an increase in both the rate constants. But due to the activation energy, the increase in the rate constant in the reverse reaction is going to be higher than that of the forward reaction, and therefore the reaction shifts to the left. So at this point, recalling that the equilibrium constant can be written as the ratio of the forward and backward rate constants. Well, the equilibrium constant is going to drop with an increase in temperature. And because the reaction shifts left, the product is consumed and reactants will get formed. And then at equilibrium, these rates are going to be the same and remain constant. And since there's an abrupt drop in the equilibrium constant with an increase in temperature, then the reaction quotient will be higher at this stage. And while the reaction is shifting to the left, product is being consumed and reactant is being formed. So the system is basically bringing the reaction quotient into agreement with the new equilibrium constant. The rate of forward and backward reaction is plotted below for a reversible reaction. Identify the time when a system is stressed in the equilibrium state. Determine if the equilibrium constant will change and the type of stress. Well, the system is at equilibrium when the rates are equal, so it's being stressed at this time over here, which we'll call Ts. And in this case, the equilibrium constant will not change because the rate of the forward reaction is equal to the rate of the reverse reaction at all times, since equilibrium was established. So there's no change in the equilibrium constant. And if the stress was due to a change in temperature, then the forward and backward reactions will change by different amounts. But since they increased by the same amounts, then the stress must have been due to a catalyst, which increases the rates of both the forward and backward reactions.